Hello, everyone. Welcome to Freebirds Classes. And today we'll be looking at a very interesting and very important proof of the fact that pi is actually irrational. Now, let's first start by seeing or remembering what is pi? Pi is the ratio between the circumference of a circle and its diameter, which means that if you draw any circle with a diameter d, which can be any real value, then the circumference would always be pi times that value. Now, this is interesting because this is true for every single d. And people have been trying to figure out the value of pi since ancient times. Why? Because you want to make a wheel, you need to know the amount of logs that you're going to use to make that wheel. And for that, you need this ratio perfectly because you can't waste unnecessarily all the logs or steel or anything. Now, people from ancient Greek to ancient Egypt to ancient India, everybody have figured out this value of pi because it was necessary for their day-to-day life, right? But then this is a very interesting number because it's continuously and never recurring. It occurs continuously and is never recurring, which means the numbers that are after its decimal points do not ever follow a pattern. And we know that that is what's irrational. And we have evaluated until a trillion digits of this number during this time. And then, of course, it's still not repeating in any way. But we can't just say that that is the proof of the fact that it's irrational, right? Because what if we have to count another 10 trillion times and then we be like, oh, there is a pattern. It repeats after 10 trillion times. We can never know that. Even though we don't have the computing capacity, we can never know that. The only way we can know that is through the laws of logic and the laws of proof. And not just that, every single time infinitesimal or infinity, either of these come into the picture, calculus comes into the picture. And that's why we'll be showing the actual use and actual important use of calculus and also the laws of logic by understanding how they can be used to prove the fact that pi is actually rational instead of trying to build the computing power to just constantly evaluate a million trillion gazillion digits of pi. So this proof was actually first given by Ivan Nithin, a mathematician, in 1947. Interesting year. And this is it. You see the proof here? This is the proof. And it's interesting how it was literally just one page of proof, but then if you try to make sense of it, it's not going to be that easy. You have to expand upon this. You have to see why he's making this step or why he inferred this from this, right? And that is what we'll be saying today. And hopefully, by the end of this session, you can read this single page and then understand all of his steps perfectly. Now, this is what I've started with, right? Or more like in my own understanding or an elaborate proof of this is what I started, and this is what Niven started with. He started with the fact by assuming that pi is actually rational. He says that pi, or assumes that pi is equals a by b, and a and b are integers, right? And b, of course, is not equal 0, right? Now, this is where things get interesting when you get into proof theory, because when you read a lot of proofs, at least at the higher levels, there'll be these random functions or random assumptions which will be made, which will not make sense until the end, right? And we'll follow the same thing. We'll look at the function, we'll get through the proof, and then you'll understand why this function was picked. Anyway, so he decided and defined this arbitrary function where n is a positive integer and this is that polynomial. And this has been chosen specifically for three properties which we need to get to this proof or get to the end of this proof. Property one is symmetry. That is, if we put pi minus x in the place of x, which is actually a by b minus x from here, you get the exact same polynomial. Look at it, try to do it, right? That is, all we have to do is make f of pi minus x equals a by b minus x power n into a minus b times a by b minus x power n divided by n factorial. If you try and simplify this, you will get your value again as f of x. So this is a very important property which is necessary, right? So let's get to the second property. So this is a little complicated, but first let's read what the property says. If we expand the numerator of f of x, right, it's a polynomial function. It's a polynomial function. The lowest power would be x power n and the highest would be x power 2n. Why? Because this is a polynomial of degree at least n, and then this is a polynomial which is getting multiplied by x power n. So it will be at least x power 2n, right? And given that this is all integers, right? So it's highly possible that's going to be x power 2n, right? Now, when you evaluate f of x and all of its derivatives at x equals 0, what does he mean by all of its derivatives? We'll see soon. The results are strictly integers. Because of the symmetry, the function and all of its derivatives evaluated at x equals pi are also strictly integers. This might be a little complicated or gibberish to some people, but let's take it one step at a time. This is what we're trying to show. We're trying to show that both of these are integers for k equals 0 to 2n. What is this k? Actually, this k is the nth derivative. So we know that f of x exists. Sorry. And this becomes f dash of x while we differentiate it. And if we differentiate this, it becomes f double dash of x, and then triple dash of x, and so on. And this k is the kth derivative, which means here k equals 2, here k equals 3, and so on. We can have k till how much ever we want, and that's called the kth derivative, right? So now what we'll do is, let's first try to understand what is going on here. The kth order derivative at 0 for all values of k up to 2n is what we're trying to prove to be an integer, right? And same thing with a by b or pi, right? So now first let's look at 0, right? We're going to take our function f, which is this, right? And then expand this polynomial out, right? So for a minus bx power n, it'll be a minus bx into a minus bx dot 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 till n times, right? And that will give you a polynomial with integer coefficients, because remember, a and b are integers, as we saw from pi equals a by b when we defined it as a rational number, right? So now all these coefficients are also going to be integers, right? So when you do this, you'll have a constant term, a linear term, a quadratic term, all of that. And then that is getting multiplied by x power n. So till n degrees, you have a polynomial and that is getting multiplied by x power n. Now this again, as we said earlier, becomes x power 2n, right? And the key here, as I said earlier, again, is the fact that cn plus 1 are all integers, right? We have not introduced any fractions this way, right? And you could figure out what these CNs are using, say the binomial theorem, but we don't have to do that, right? All we need to know is that CNs are integers. And now let's distribute 1 by n factorial, right? And now this becomes a fact, and now this becomes, a fraction. Clearly, and I hate saying clearly, we can see that f kth derivative of f at 0 will be 0 for k from 0 to n minus 1, right? Why is that? Because if we take the derivative of all these terms, they're still going to have x's in them, right? All the terms are going to have are at least x bar n. And if we keep taking the first derivative, this will become n x bar n minus 1. And then there's going to be x bar n minus 1. And then so on and so on and so on. And they're always going to be, right? Always going to be 0, because if there is an x term, all of them cancel out. All of them become 0, right? But then notice what's happening here. When it becomes the nth derivative, right? When you take the nth derivative of this term will vanish. As for example, let's see here, f of x equals x power 5. Let's say that's the function. The fifth derivative of f of x is actually 120. It's a constant. It's not, it doesn't have an x term. And if you put x equals 0, this does not vanish. This still stays, right? And then continuing on, so that the only coefficient that will be left will be Cn and everything else will vanish. And then after this, if you derive, after this, what will be left is Cn plus 1 into n plus 1, because this will vanish now, right? This will vanish, this constant will vanish, and this constant will remain, and then this constant will vanish, and this will remain, and this constant will vanish, this will remain. So like this, it's always going to be either 0, the nth derivative of f, or an integer like this, because n is a positive integer, c is an integer, as we saw from this definition. So integer into integer is an integer, or it's 0, right? So this is how we prove this fact that it is actually strictly integers, right? Strictly integers. Now let's get to the property C, which is an important property, which is that strictly between 0 and pi, both x and a minus bx are actually positive. Therefore, f of x is greater than 0. Furthermore, f of x has a maximum value on this interval. The maximum of x into a power a minus bx is pi a power pi a by 4. What is this? This is just taking out maxima and minima, right? It's just saying x minus a by bx, the maxima of this function, take the derivative of this and then put it at 0, and then find the maxima, you get this. But then for simplicity, we can just say that, hey, x is going to be less than pi because it belongs to this interval, and a minus bx is going to be less than a. So it's going to be less than this, right? If we substitute these two terms here in the original polynomial, that is x equals pi and a minus bx equals a, it becomes like this. This is for simplicity purpose. That's what we say now. But then in the future, when we get to the end of the proof, it will make more sense. Now, we have seen these three important properties, right? The defining properties. Now let's get to the magic, the calculus magic, and that's why I titled it as calculus magic. Now let's define a function, capital F of x, consisting of small f of x and its even derivatives alternating in sign. Why? We'll see why. So capital F of x would thus be f of x, f double dash minus f double dash of x, plus f fourth derivative of x, minus f sixth derivative of x, and so on till minus 1 power n f 2nth derivative of x. Why do we do this? Because see, if we take the second derivative of this capital F, right, what's going to happen? This is going to become f double dash of x. This is going to become f fourth dash of x, and then so on. And the only thing that's going to be left is f of x, right? That's the only thing that's going to be left. So this identity will hold no matter what. One second. All right. So this identity is something very important. Now we introduce trigonometry and integration. Why? We'll see again. So dy dx of this function, we're going to get that. Why? So let's just do the derivative and then see this, right? So f dash of x sine x minus f of x cos x, right? And that expands to f double dash of x sine x plus f dash of x cos x minus f dash of x cos x minus f of x sine x, right? And then if you expand it, this is what we'll end up with. Notice something funny about this? This is f of x. So therefore, this derivative of this function is actually f of x sine x. Simple. Now, why are we doing this complex arrival at this term f of x sine x? We'll see again. Now, let's integrate this function, right? From 0 to pi, because we have taken from property 3, when we have defined it to be between the interval 0 to pi, it has to be used somewhere. Like here is what we're using it. So it's going to be integrated from 0 to pi, and it's f of x sine x dx, integral of this function. And it is this. Why? Because when you integrate a derivative, it's going to give the function. And that's exactly why we did this complex stuff. And how did we arrive at that? How did the proof maker would have arrived at that? He would have started here actually, right? And then differentiated it or integrated it, right? And see what would have been the value of a function that would arrive at when we differentiate this, integrate this, and that's what he got. So it's reverse engineering, but then when we read the proof, it's like, oh, where did this come from? But then when you think about it intuitively, you get what this is. Anyways, moving on. Now, this is what we get from the interval 0 to pi, because these two things cancel out, right? So this is remaining. Now, let's evaluate this, right? So at x equals pi, sine pi is 0, as we know. This is the graph of sine, 0 to pi, it's positive, right? And this is the graph of cos, right? Pi by 2, 0, right? Anyways, sorry. This is not pi by 2, this is 1. This is 1 and this is pi by 2. This is minus pi by 2. Anyways, so at sine pi is 0, cos pi is minus 1, and the term becomes f pi, and at x equals 0, sine 0 is 0, cos 0 is 1, and the term becomes minus f of 0, right? And then when you subtract these two, when you substitute the terms, you get this as the value of integral. Now let's go to the key of property 2. What does property 2 say? It says that f of x and all of its derivatives are integers at x equals 0 and x equals pi. Remember that? Pi is a by b. And then by symmetricity, we proved that it's the same as pi minus x, right? So what do you get? You get the fact that at x equals 0 and x equals pi, it's just a sum of these derivatives, and sum of integers is what? Another integer. So this is an integer, this is an integer, right? And what happens here? And this would evaluate that this makes the whole integral to be an integer, right? If you miss the fact that when I said that at pi also it is an integer, f of x equals f of pi minus x. So when you put f of pi, this would if x equals pi, this will be equals f of 0, and thereby f of pi equals f of 0. Anyways, coming back. So now we have proved that this integral would be a integer, right? Keep this in mind. Now coming back to the contradiction, this is the important and the key step of the proof. Now f of x is greater than 0, right? Because n is a positive integer, right? And sine x is also greater than 0 in the interval 0 to pi, right? If x is between 0 to pi, x is positive, and if x is positive and n is positive, what's going to happen? X is the function f of x that we saw over here is positive, greater than 0. And sine x is, of course, greater than 0, as we saw here from 0 to pi, right? So because we're integrating a strictly positive and continuous function over a positive interval, we know that polynomial functions are always continuous, right? The area under the curve must be greater than 0. And what is the area under the curve? An integral. The definition of integration is area under the curve, right? So this is greater than 0. But we also bounded the maximum size of f of x, right? So, which is f of x, well, we said that it's less than pi power a by a power n by n factorial, and maximum size of sine x is 1. So f of x sine x should be less than this. And the integral of function would therefore be also less than this, right? That is, the integral must be smaller than the maximum height of the area times the width of the interval, which is pi, right? This is where the proof gets to its zenith, right? This is where it's going to flip. The calculus, the factorial function n factorial grows significantly faster than the exponential function. Why? Because see, the numerator is pi power n, which is pi into pi into pi dot 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 dot. And the denominator is and the denominator is n factorial, which is 1 into 2 into increasing numbers constantly. And also we have this a into a into a into a. And if n keeps on growing to some infinity, right? If we keep increasing n, the factorial is going to grow much faster. It's very intuitive to see, right? So if we choose n to be sufficiently large, then this will be less than 1, right? Because the numerator grows slower than the denominator. So this fraction would be less than 1. And we also said that it's greater than 0. So this integral would be between this interval, no matter what, right? And that's where the contradiction comes in. We just proved over here that it's an integer. And we are also saying that it lies between these two, 0 and 1. It cannot go beyond this. How is that possible? How can an integer exist between 0 and 1? It's not possible. And every single mathematical step that we did was true, was logical. So where is the flaw? Where has to be the flaw? Over here. When we assume that pi is rational. Therefore, pi by induction or reductio ad absurdum, it's irrational. This is what Nithin said in one page. It took us nearly 25 minutes to understand that. But the key is this, right? When you develop the intuition to see or to understand or to find something or to even apply the fact that okay, this is continuously increasing, this is saying okay, this digits, the decimals are constantly growing towards infinity, they're not repeating at all. Oh, okay, infinity. What do I apply during infinity? Okay, maybe something infinitesimally small, something polynomial, because the Taylor series, and various series through which you can evaluate the value of pi. Pi by 4 equals 1 minus 1 by 3 plus 1 by 5, all of that. So you think, okay, so it has to be something related to binomial. So it has to be polynomial. And we also connect calculus to it. So if you keep thinking in this way, which is what Nithin did, and he was, of course, a much more accomplished and experienced and skilled mathematician, he arrived at this proof and reverse engineered it. When we read it in the beginning, we were like, okay, what is this function? What is this? Why are you assuming this? Why are you taking a derivative of this? This is all coming from the reverse engineered idea. And of course, when we write the proof, we have to be logical. We have to try and make it simple, and we have to try and make it ordered, right? Because he's submitting it to, as we saw, Purdue University, Purdue University, which is an important established university. So it has to be logical. But then the thought process is not like that. The thought process is actually much more different. It's by thinking about, okay, infinitesimal means calculus, polynomial, binomial means calculus, pi means binomial. Okay, how do we connect all of this? It's how do we connect the factorial? Because in a lot of these series, you get factorials, right? So many people have expressed before me, I mean, thinking as Nithin, that pi by 4 is the sum of these factorials. So how do I link all of that? That intuition is what is necessary in math. And when you get that intuition and then apply it in every other subject, physics, chemistry, biology, economics, anything, that's when your study is complete. And that's what we'll be trying to teach over here. And that's what you'll be learning if I teach you anything. I hope this was very informative to you. And I'm looking forward to see you in the classes.